So this is the contents of 3 lectures that I'm planning. Today I'm going to explain to you, yesterday I explained to you some aspects of large supersymmetric AdS black holes from a Cardi-like formula of maximal super Young-Mills. Today I'll try to go beyond the large black hole limit and see what kind of more exciting things we can see. So this is a very, very brief summary of what we did yesterday, just in case somebody missed yesterday's talks. So I consider the index of maximal super Young-Mill theory, counting 1/16 BPS states with 3 electric charges, 3 R charges, and 2 angular momentum. And the chemical, it's slightly in the unconventional form that it doesn't have -1 to the fermion number explicitly, but its effect is reflected in my convention into the relation satisfied between these chemical potentials. So this 2 pi I instead of 0 reflects the effect of -1 to the F. It's purely technical setup, but it makes things look much more nicer. Okay. So the suggestion made yesterday is to consider the large n, but also consider the large charge limit in which the angular momentum chemical potentials are set to be small. So try to develop a higher dimensional analog of the Cardi formula of 2-dimensional CFTs. An important aspect that has been emphasized was to keep the order 1 part of let's say, imaginary part of chemical potentials, trying to best obstruct the cancellations or smearings of nearby macroscopic degeneracies at large values of charges. Because nearby states, nearby degeneracy, we generally expect there to be some random and fast oscillations between plus and minus signs. We try to introduce phases to maximally obstruct such cancellations. So in particular in our Cardi formula, it turned out that the order 1 component of chemical potentials in the internal R symmetry charge turns out to be play an important role. Yeah.
Could I ask a question, sir?
Yeah.
In the supergravity regime,
yeah.
where n is large, but you're counting dimensions that are small, and fixed. In that regime, is there also rapid oscillation of signs?
I'll do a recalculation of what you did in the gravity index in the confining phase. The result will just be counting the index with chemical fugacity replaced by complex ones. So in the confining phase, I find that complexification just plays a very trivial role.
Right. I see. I see. And so, shall I interpret that as saying that all terms come more or less with the same sign?
Of course, they also come with minus signs if you expand the known gravity index. I'll explain to you later, but all I observe is that I get the same gravity index that you got with just, chemical potential factor just complexified.
So suppose I try to extremize that with respect to the complex part of the chemical potential.
To get to the microcanonical graviton ensemble.
I was wondering. Would you?
One can try that. One can try that. I never thought about that, but there might be complex saddle points which give more interesting information about graviton itself. I haven't tried that exercise, but well, possible. The key idea is to search for all complex saddle points if you go to the microcanonical ensemble. So it might play a role in gravitons, right? But yeah.
Also, another thing is that just to kind of
yeah.
the basic idea.
Yeah.
You say that you introduce phases. That also makes sure that you never count something more than it could have contributed to the partition.
Oh yeah. Still, yeah. Structurally, it can never happen. But I mean, on physics grounds. So we expect it. I mean, even though we partially obstruct such cancellation, we still expect the computed entropy to be a lower bound of the true entropy. In the best situation, saturating it. Okay. So the result that we got after this kind of calculation was the log of this index in the asymptotically becoming n squared divided by this small Cardi factor and multiplied by this electric charge, internal charge chemical potential. And these are required to carry order 1 imaginary parts forced by this formula. So this has n squared times order 1 number divided by this large charge factor. Okay. So I explained to you that this free energy, Cardi free energy, counts the known black hole's entropy in the large black hole limit when the charges are much larger than its central charge of the system. Today we'll go beyond the large black hole limit. Before making a field theory analysis,
I I'll
Yeah.
just
Sure.
say again,
Yeah.
it's what you said, but I'll just repeat it.
Mhm.
That if you go to asymptotically, could it, if you just count all supersymmetric gravitons, the partition function over all supersymmetric gravitons, that's an easy thing to do.
And you're going to compare compare it with the extremized result.
At asymptotically large charges, presumably.
Asymptotically, just with graviton effect, ignoring the confinement or thing.
Yes, exactly. So you keep all your deltas large compared to 1.
Delta is what?
compared to n squared,
Delta is what?
all your scaling dimensions.
Okay.
So we've gone to there's some large something, but large compared to 1.
Mm-hmm.
And now you could ask whether by fooling around with with your complex part of the chemical potential,
Mm-hmm.
we could just get the same answer as just the partition function of supersymmetric gravitons, which of course it's some dimensional gas, right?
Yeah.
Maybe 6-dimensional gas or something. It's 2
Yeah.
derivatives
Yeah.
and 3 holomorphic fields.
Okay.
Yeah, so it sounds like a 6-dimensional gas.
Okay.
The index grew much slower
Mm-hmm.
in the gravity
Yeah.
sector.
Yeah.
I wonder if your complex saddle point could recover the whole 6-dimensional gas wave.
That counting is a half BPS. You can count this without minus 1 BPS.
It's very easy, right?
Yeah,
Because just multi-trace,
Yeah.
you know all the single traces, and then do Bose exponential.
Mm-hmm.
We have it in our paper.
I see. I don't know actually. Yeah. Okay.
That would be the analog of your getting the black holes, right?
Well, but it's not clear when this will work and when it doesn't, so I'm very cautious. but it's worth a try. And
If it already starts working at delta large compared to 1, surely it should continue to work at n squared.
Okay, I see. Okay. So anyway, I want to go beyond the large black holes and do the field theory study later on. But let me try to explain you the following things first. I try to explain to you that the free energy that I derived in the grand canonical ensemble for small chemical potential can be, if its chemical potential is small, it can be Legendre transformed to explain the large black hole's properties. But very much like let's say, the Strominger-Waffer black hole, whose properties can be formally extended away from, whose properties derived from Cardi formula can be formally extended away from the Cardi region, but still formally gives the same result. Even the result derived from this Cardi formula turns out to explain the known supersymmetric black hole solutions property away from large black holes. Okay? So even the charges of order n squared times some order 1 number, this free energy Legendre transformation is known to give the black hole properties. This has been actually first shown by Zaffaroni and company. So before examining anything new, I forgot to erase these things. Before examining anything new, let us just study the properties of known black hole, sticking to this expression at not so large charges. So for simplicity, let us consider a sector in which all 3 electric charges are equal, all 2 angular momentums are equal, okay? Or impose these relations on chemical potentials. And in this case, imposing the chemical potential relation for the index, one is only admitted to have 1 chemical potential omega, which is conjugate to, I tried to add this summary of yesterday's content for Abhijit, but I then decided to move it to previous slide and forgot to erase this, so this is the reason for this mess. But anyway, I introduced only 1 chemical potential omega, which is conjugate to Q plus J multiplied by 2. So inverse of omega is sort of playing the role of temperature in this BPS sector. This Q plus J is sort of playing the role of BPS energy, although it's not precisely the one. So you can investigate the relations between this temperature, energy-like quantity, and the free energy divided by n squared to see some structures, thermodynamic structures of these black holes. You find surprisingly similar structures as the AdS Schwarzschild black holes I explained to you yesterday. It has 2 branches beyond certain value of temperature.
Just to understand, the Q's are all equal?
Yeah, all equal, yes.
And the J's are
all equal, yeah.
Equal, and you're coupling to Q plus.
Yeah, the index, yes. So it's what one first has a small black hole branch. It has a negative susceptibility, so it's unstable in the grand canonical ensemble. It has a large black hole branch, which is stable, has positive susceptibility. You investigate the free energy as a function of temperature. Okay? Small black hole branch I'll ignore. The large black hole branch, right after its nucleation, it has positive specific heat, so it loses against the graviton saddle point. But as you increase the temperature-like variables a bit more, suddenly it changes signs in the free energy, so it becomes more dominant than the graviton saddle point. So this point will be the BPS analog of the Hawking-Page transition had the saddle points been the gravitons and this black hole only. Okay? So the Hawking-Page transition is determined by the first black hole, which turned out to beat the graviton saddle point, which you increase the temperature. So had this been the older black hole solution known in AdS 5 times S5, the Hawking-Page temperature, inverse of that, Hawking-Page chemical potential would have been this. Okay? Now, later on, if I do a further field theory studies, I'll find a contradiction to this Hawking-Page transition. Namely, I'll be giving some evidences that the deconfinement transition of the field theory has to happen at a temperature below this. Okay? This probably, I think, predicts new black hole saddle points. But until that moment, please remember this. Okay? So I'm going to make two studies going beyond large black holes in field theory, okay? Especially having in mind whether there can be other black hole solution saddle points which can possibly dominate over the analytic black hole solutions that we know if you go away from Cardi limit. I'll try to show evidences that there could be more dominant saddle points in particular setting, various settings, and we shall discuss two evidences. First of all, I'll try to study the index in a particular subsector of the 116 BPS operator space in the so-called McDonald sector. Okay? So the limit of the index that you have to take to project to such states is called the McDonald limit. The operators belonging to this sector is called the Shaw operator, which I'll explain shortly. Secondly, after explaining the first point, I'll try to revisit the question of deconfinement using this eigenvalue distribution viewpoint, incorporating the idea of complex phases. So let us first study the 1/8 BPS McDonald sector.
So here,
Yeah.
N is taken to infinity
What?
in all this analysis.
What is taken to infinity?
Capital N. Or
Yeah. But when I make a Cardi-like analysis, large charge is playing more important role for doing saddle point. Of course, I take N to be large as well, but N to be large and charge be much larger than the N square. Yeah. So at last stage anyway, I send N to be large.
because on the gravity side, we expect a Hawking-Page transition in the project.
Yes. Yes. So in the Cardi formula that I have been using or I'm going to use is the large charge regime in the larger limit. So you're way beyond the Hawking-Page transition temperature, deep inside the deconfining regime.
The high temperature.
Yes. So to be a little bit more, so 1/8 BPS sector is obtained by imposing extra conditions on the 116 BPS operator's condition, energy being a linear sum of these 5 charges. And just for, there turn out to be 3 essentially inequivalent 1/8 BPS sectors. 2 of them are in some sense boring, in the sense that they are not expected to host black holes. Last 1/8 BPS sector are somewhat more non-trivial, and I'll claim that there should be existing black hole-like saddle points, even in some special subsector.
Sorry, you assign particular chemical potentials to black holes.
Chemical potentials to black holes. Where?
In the
Previous slide?
Yeah, previous slide. In the previous slide, we've got, let's say we were just doing black hole analysis.
Yes.
So let's say you had no field theory information.
Yes.
So we know the black hole solutions.
Yeah.
In order to understand some sort of partition function, you will need to know what the chemical potentials for these black holes are. How are you doing that? How are you getting that?
How am I getting that?
Yes.
The chemical potential from black hole, the gravity side.
Yes.
Well, I start from near extremal black holes, slightly away from the BPS ones.
And
So,
take the limit,
yeah, and there the chemical potential has to be computed and take the limit. I always compute it that
So
way.
your chemical potentials this way are always real?
Yes. And it agrees with the real part of the field theory complex saddle point. I mean, that's another check of the field theory gravity agreement.
So when you draw this diagram, this is always for real chemical potential.
Oh, yeah, it's always the inverse of the real part. Yes, of course, yes.
Yes.
Inverse of the real part,
Thank
yeah. Sorry, I didn't, oh, yeah. Here, this denotes real of omega, sorry. Yes. Good. Any other question? So, there turned out to be 3 inequivalent 1/8 BPS sector, which I decided to explain just for completeness. On top of this condition, if you impose the condition that summation of the 2 angular momentum becomes 0, this defines the famous chiral ring sector. This sector is completely solved, and the spectrum is not rich enough to host black holes. Okay? The sector with two electric charges summing to 0 defines another equivalent BPS sector. It's already also completely solved. It's known to host no black holes either. I forgot to, but I made a confusion in the literature, but I thought this work was your work, but it's Nemani's and other people's work, is that right?
Yeah, so with Nemani and then there's another,
yeah. So it's your work, right?
yes.
Oh yeah. So I didn't confuse. Okay. and Shiraz and I and collaborators made a further field theory viewpoint about this sector, but no black holes there. Third 1/8 BPS sector, called the McDonald sector, is obtained by taking one electric charge and one angular momentum summing to 0. Okay? So in this sector, operators preserve 4 supercharges. As far as I know, no complete solution of the operator spectrum is known, called Shor operators. The good point is that you can take a limit of the index, taking some of the chemical potential to be infinity, like 0 temperature limit formally, projecting yourself to the operator satisfying these further conditions. Okay? So this kind of limit can be taken. You take 1, 2 of the chemical potential to be large, actually taking their differences to be finite, and the index reduces to this so-called McDonald index, which has been first explored by Abhijit and Rastelli collaborators. In this limit, you only have 3 independent chemical potentials because you got rid of one, and it's coupling to 3 different charges. Also, the matrix integral expression can be taken a limit. It's a gauge singlet condition of some single particle partition function. Due to the fact that you impose this constraint, the second derivative contribution in the denominator somehow cancels with the numerator ones, and effectively you're left with 1 derivative factors. So it's sort of, it behaves like 2-dimensional partition function in a sense. Okay? So we call this a McDonald index. So I'm going to, yeah. I think, I once checked it. If you take the further Shor limit, only finding one combination, I think the cancellation happens too much, so apparently result you see is very boring. Yeah.
The derivative is still there, though.
Derivative still there. So what is the it's a Shor limit? I forgot.
Language I will not be able to
Yeah. But if you further impose Shor limit in anything that I'll be telling you later, you can either cannot impose it or result becomes boring. Yeah. So having full chemical potential is very important. Okay. So I'm going to investigate what the large N and especially some large N Cardi-like behavior of this chemical potential is, because with my technique, investigating just large N is a bit tricky at the moment. But let us first examine what we expect in the McDonald sector on the known black hole solutions. Okay? I explained to you that the 4-parameter solution for the black holes carrying 5 charges have to satisfy a charge relation. One can study the implication of that charge relation, it's very complicated, by further imposing this McDonald sector condition. You can impose this condition and the more complicated charge relation condition and play some games, and then the charge relation becomes rather simplified into this form. Okay? So this tells us many things about the fate of the black hole solution, the known one. The first factor here is manifestly positive, it's non-zero. The second factor is, I claim, is an addition of 2 non-negative terms. The first combination apparently looks not positive at all, but if you recall the expressions for the Bekenstein-Hawking entropy of these black holes I explained to you later, this combination is nothing but the square of the entropy of black holes. So if you're going to keep a regular black hole with finite horizon area, this has to be non-negative or positive. Otherwise, the solution is just singular one, or at best small black holes. Q3 square is obviously positive, non-negative. So the charge relation, together with McDonald index sector condition, demands that Q3 is 0, so that Q3 and J2 are separately 0. So in a sense, this is the black hole charge relation. But on top of that, you get a further interesting condition that the entropy of the black hole, if you go to the McDonald limit, has to shrink to 0. Okay? So the horizon shrinks to something like small black holes. So this solution itself might be very interesting. For instance, invoking the stretched horizon picture of Ashok, you can do some interesting studies there, I think. But for the purpose of studying regular black holes, one can say that there are no black holes in this sector among the analytic solution. Similar conclusion can be obtained more abstractly from using this free energy, but let me not do that because it arrives at it leads us to equivalent conclusion. Now with this in mind, we're going to investigate the Lagrangian behavior of this McDonald index. But similar to the spirit that of yesterday's lecture, I'm going to consider what's called the McDonald-Card limit. Okay? So I have one remaining derivative chemical potential left. I'm going to study a large charge regime in which this omega 1 is supposed to be small. Okay? So
one of them is large, one of them is small?
Yes, yes. Omega 2 is large. That's part of the definition of McDonald index. So I'm definitely deviating myself away from the four-dimensional card regime. Okay? But another derivative can be kept to be arbitrary thing, and I'm going to investigate a simplified regime where we take a kind of two-dimensional card limit to be distinguished from the four-dimensional one. Okay? And there, if you assume this, the technical analysis gets very, very simple from the previous ones. So you approximate this derivative factor into n times omega 1, of course with some cutoff issues that have been raised yesterday. And then you get the characteristic 1 over omega factor in the asymptotic free energy. You again find that the maximally deconfining saddle point is at least locally stable saddle point. So impose this condition, the integral is gone. And the final free energy that you get is n squared divided by omega 1 multiplied by this linear combination of dialog functions, because you get summation of n times 1 over n times another 1 over n coming here, which is a definition of dialog functions. Now I'm going to use this Cardi like 2D McDonald Cardi free energy, of course with large n limit taken, to go back to the microcanonical ensemble. The equation of this is this. Again, you have to find a complex saddle point to find something non-trivial, but it's too complicated to me and my students. So we essentially need to rely on numerical analysis to study these equations. Okay? Luckily, I have a very powerful student who can do this job, almost analytic calculation, but using numerics at a really last stage to give me quite a confidence that this solution he found was the right one. So the numerical solution that we found is the following. Just for the simplicity of displaying, just for the simplicity, we have considered a case where two electric charges are equal. So setting that on refinement doesn't lose many things. So basically, it's a kind of equal charge case in the McDonald sector. So you have basically two charges, one electric charge and one basically angular momentum, all divided by n squared, and entropy divided by n squared. You plot all these things. Okay? In particular, I plot various quantities at given large value of angular momentum because I'm in the Cardi limit. Okay? For instance, if you change the electric charges, you indeed see that you find positive macroscopic entropy. Okay? Up to the point I denoted by dashed line here. Beyond the dashed line, something weird will happen, which I'll briefly comment on. Okay? Anyway, in this region, we find macroscopic entropy, and all the temperature-like chemical potentials, the real parts are positive. And we also check that the stability of this large n saddle point in the grand canonical ensemble, basically checking that it has positive susceptibilities by computing Hessians and so on. Okay? So this seems to be really robustly predicting new black holes in the McDonald sector, at least in the region where the angular momentum charge is large, contrary to what we have found on known black hole solutions. So this I'd like to claim as an evidence that a new black hole-like saddle point should exist. The one first evidence. Good? Any questions so far? It looks very complicated, but yeah. So this is the concrete thing I can say about this system. I should comment on one.
Sorry,
yeah.
sorry,
Yes. Yes. Sure.
I missed the details.
Yeah.
Is this the analog of the free energy going negative somewhere?
Free energy going negative. Oh, this is the kind of this is the kind of two-dimensional Cardi regime with large charge regime. So if you consider free energy there, it's always negative. Yeah. Yeah.
Sorry, please. I was spacing out.
Oh.
So you have these. You want to claim that there's a new deconfining saddle point.
Huh?
So you have to compare this with just the gas, right? In this limit.
Free energy of the gas.
Yes.
Which will be order n to the 0th power.
Right. So the fact that this free energy is negative already tells you
that it's dominant at least over that gravitons.
Yes.
Yeah. Well, it's natural because anyway I'm investigating the Cardi regime, so it should be it's sort of large black holes in this region. But anyway, we check that it's negative. It's quite.
Yeah.
It's not in the table, but yeah, we checked it's negative. Yes, yeah.
So this dotted line is the one in which the susceptibility flips sign.
Yes, so it's kind of, yeah, so that's what I was going to mention. But a very weird aspect that happens is that if you fix the angular momentum and increase the electric charge, the inverse temperature diminishes to 0. So at finite electric charge, it turns out that the temperature-like variable diverges to infinity and then flips to negative temperature-like regime. So I don't really know what this is. Probably it's meaningless saddle point in the grand canonical ensemble. But the weird fact is that you arrived at, in the grand canonical ensemble, the system seems to be meaningful at maximal value of electric charge set by the angular momentum. That is the queer behavior that we found. And that seems to be a little bit similar to, at least qualitatively, a little bit similar to some properties that have been found in the hairy black holes, non-BPS and BPS hairy black hole ones, in AdS 5 times S5. Although they have studied a very different sector than the McDonald sector, and probably I think the small black hole branches were studied, a somewhat similar behaviors has been found in that if you try to take non-BPS black holes and try to reduce the electric charges onto the BPS bound, below a critical electric charge, you find that the configuration is quite nice in the canonical ensemble, having 0 temperature limit. In the supercritical region of electric charges, in this kind of solution, you find that if you reduce the energy, you find the temperature is diverging in their numerical studies of Santos and Markevich-Ute. So I find that in canonical ensemble, these solutions exhibit a somewhat similar property, that it meaningfully exists only with maximal value of electric charge set by angular momentum. This is just vague analogy that I feel, but I don't know how to make this idea sharp. I just feel vaguely that the weird aspect is somewhat similar to a characteristic aspect that people have found in the hairy black holes business.
What kind of supersymmetry do they preserve?
Here. Here, generally, it's 116 BPS. It's all equal electric charge, equal angular momentum. So it's really different from McDonald sector. But the mere fact that there's a maximal value of electric charge for canonical or grand canonical ensemble makes me somewhat vaguely tempted to suspect these might be somewhat similar behavior. But it's very hazy statement, yes.
Could I ask a related question?
Yes.
At least roughly, you expect black holes to undergo superradiant instability when the chemical potential times charge of some graviton becomes larger than its energy.
Larger. Okay.
So now your chemical potentials are basically 1 plus 1 by beta.
1 plus 1 by beta.
Because your chemical potentials for the supersymmetric black holes will just be all 1, 1, 1, 1, 1, 1.
Yeah.
But the things that you're quoting are the coefficient of the 1 by beta.
Yeah.
Now, I was wondering if one kept track of that 1 by beta. Could one check whether there are some gravitons under 1, all gravitons that preserve the same supersymmetry will have Q times chemical potential equals energy, because it will just be the BPS bound.
Yeah.
Okay, so they're right at the edge.
Oh, the correction might be telling you.
Might turn you one way or the other. And I was wondering whether that would help us understand what kind of hairy black holes we should expect.
I see.
The mode for which, if there are modes for which this goes negative,
Yeah.
you should expect those modes to condense.
I see. Sure.
So just to say again, you have this property of these black holes right at the beginning. You had the Hawking-Page transition.
Yeah.
You had gravitons going up to a point, and then black holes after that.
Yes.
But before we reach the edge of the black holes, something should be going unstable, right? Because you say you're going to find evidence that
Yes.
it would be nice to see what the first instability is.
I see.
Maybe not so tough.
You mean starting from black hole and reducing the temperature?
Starting with the place where the black hole is stable.
Yeah.
So they high temperature.
So reduce temperature and
Reduce
find
the
Harry's
temperature.
instability.
At some point, you should be able. You should go to some values of chemical potential where some graviton becomes super radiantly unstable.
But so this is why I don't understand well. But if you have hairy BPS black hole, the superradiant instability which causes that hairy BPS black hole, the starting point, couldn't it be the non? The starting black hole should be BPS and non-B.
That's where it first happens.
Yeah.
But if you go all the way down to the BPS limit, that should by itself be unstable.
Okay.
Right, because it should not be the stable guy. It should want to emit.
I see.
So this 1 by beta is a bit confusing.
Okay.
So I'm not sure how. But at least roughly one could. Okay. Yeah. At least roughly one might get some intuition for what's going on.
Okay.
Just by doing this for the data.
Okay. Thank you. I'll talk to you more then. Okay. So this ends the first part with a rather hazy comment. But I think in the McDonald's sector, it's really a black hole-like saddle point, so we should think about it more seriously. And then let me turn out to the second topic. Namely, I'll go back to the deconfinement transition issue that we have discussed yesterday. This is just a basic summary of what I told you. Yeah.
I mean, this N squared you don't see in this free energy?
Free energy, N square? Here N square.
Okay.
Yeah, and I plotted all the quantities divided by N square. So it's order 1, yeah. Okay. So just, I told you, yes, yeah.
One more vague question.
Yeah.
It's probably stupid, but could any of these supersymmetric black holes have a Gregory-Laflamme type instability?
You mean in the internal S5? Is that usually happening for small black hole region? Or?
It usually happens for small black holes, yes.
It happens to objects localized in this S5.
Yeah.
Could it happen or not? I don't know.
If suppose you find that the instability occurs equally for all modes of the scalars. Trace phi to the n.
Yeah.
All the chiral primaries like trace phi to the n.
Oh, these are harmonics on the phi space.
Yeah. That might suggest that it's localizing.
I see.
But it might suggest the actual supersymmetric black holes. I don't know if it's possible. It's a vague thought. It might suggest the actual supersymmetric black holes are very different from those of gate supersymmetric.
But you have kept a truncation down to trace phi square, right?
We kept a truncation down to trace phi square. We already saw such things happening. But now we didn't look at trace phi cube, trace phi fourth, and so on.
That's technically difficult thing.
Technically difficult. However, just this analysis about whether the gravitons are going unstable. If we believe this criterion of mu times charge is greater than E, that can be done for everything.
I see.
It's a bit vague, but
okay. Thank you.
So you expect all these modes to become unstable at the same time or as a cascade?
Yeah, something. What happens for rotating gravitons is that the infinity guy becomes unstable first. The guy at n equals infinity, which means that if anything becomes unstable, an infinite number of them becomes unstable. Which means that something quite dramatic is happening. Here is a candidate for what the dramatic thing could be, which is localization on the that if that were happening, I have no clue. But if that were happening, it would tell you that you should work in 10 dimensions rather than 5 dimensions.
Okay. Good. Any
These
other?
are very interesting.
Yeah. Sure. Sure. Other. Good. So just to remind you, I mean, we have both in the Schwarzschild AdS black holes and also for the known analytic black hole solutions, we have identified small black hole branch, large black hole branch. And in both cases, the large black hole branch were competing with the graviton saddle point, and that can cause the Hawking-Page transition. And as a dual of that, we are seeking for the deconfinement phase transition of gauge theory. I'm repeating myself, the things I told yesterday. So I'm starting from the matrix model expression for the index. And as I told you yesterday, the large number of these eigenvalue integrals in the larger limit will be replaced by a functional integral of distribution of these eigenvalues on the circle. Essentially equivalently in my setting, I'll be replacing this by the infinite number of mode integrals the Fourier mode integrals of this distribution function, whose integrand is Gaussian. Okay? The coefficient of Gaussian, if it's positive sign, it will lead to a confining saddle point. If it's turning out to be negative, it will be a signal for deconfinement. But what we have been observing yesterday was that for the index with positive chemical potentials, playing the role of temperatures, has always positive signs, no matter how small you take the chemical potential. So apparently the index doesn't seem to be seeing the deconfinement transition at all. Or more precisely speaking, it's not seeing the point where this confining vacuum, confining saddle point, where rhos are 0, are getting locally unstable. Okay? Now the idea is to do the business again, introducing the phase of the fugacities. We have seen that introducing the order 1 imaginary part of chemical potential changed the story a lot in the Cardi limit. So we do the same kind of exercises in this Lagrangian eigenvalue eigenvalue integrals. Okay? So you do the same kind of analysis. The calculation idea is very, very simple. For simplicity, I only keep one chemical potential as before. Let's say this one. So all equal electric charges, all equal angular momentum again, so that you only get one chemical potential, Q fugacity x, which is conjugate to Q plus J, as I explained to you before. So if this x fugacity is real, obviously this function coefficient is positive, so it doesn't see any phase transition. The simple thing I'm going to do, and it's a very stupid exercise, I'm going to do is to replace this fugacity by a complex one. This is the fugacity, and this is the phase that I'd like to dial to maximally obstruct the Bose-Fermi cancellations. Okay? What I'm going to do is to dial phi to an interesting value and see whether this rho eigenvalue, it turns out that rho 1, the fundamental representation, the Polyakov loop in the fundamental representation, condenses first. So dial this so that whether rho 1 can condense. Okay? So rho 1 being 0 will be unstable if real part of this function is positive, but it will turn out to be unstable if the real part turns out to be negative. The strategy is that, depending on phi, value of phi, macroscopic cancellation between bosons and fermions may be partly obstructed. Okay? So the phase transition apparently visible by the index may be less delayed. So the naive strategy that I'm going to take is to dial phi into an optimized value to seek for or find the least delayed transition. Okay? Trying to interpret it as an upper bound for the instability point of the confining saddle point. Okay? So this is the...
What do you mean by delayed transition?
What?
What do you mean by least delayed transition?
So if you see macroscopic entropy, e to the n square, boson plus fermion, it will trigger some phase transition at a certain temperature. But if due to minus f, this growth of, apparent growth of degeneracy visible by index is much slower, somewhat slower, then the apparent transition visible by the index, one can naturally examine is delayed. If the cancellation is so severe, it may be delayed to infinite temperature. So I'm going to obstruct the cancellation as much as possible.
The smallest...
Yes. I'm just trying to map these two, connect these two phenomena together. Yeah. So this is the real part. This simple function, insert this, just extract out the real part with mathematical, you get this expression. For your convenience, I first plot on the x phi plane, phi x plane, the curve where real part becomes 0. It's very stupid, sorry. It's a very stupid function, but it's given by this red curve bounding two dome regions in which the real part has negative sign, and outside this red curve, the real part is always positive. Okay? So going back to 0 phase, the original setting in which the calculation has been done with real fugacity, the sign of the real part is obviously always positive, so you don't see any signal for the instabilities of the confining saddle point. You gradually increase the phase, nothing happens, it's still positive sign all the way to infinite temperature. Only after you turn it beyond the critical value, you suddenly see a less delayed instability at finite value of fugacity. Okay? The optimal way of tuning it is to have the phase angle exactly at the two tips, whose value is either this, I have an analytic expression, but approximately this, or it's 2 pi conjugate, flipped version, here or here. Okay? So at this point, the least delayed instability point, transition or instability point, turns out to be this. So this is nothing but e to the minus 1 omega, some temperature-like variable in the index. So it's the corresponding fugacity. Okay? So I'd like to interpret that as an upper bound of deconfinement because the confining saddle point, at least at this point, becomes locally unstable. So some transition has to happen at or before this point. Okay?
What are the modes that condense at this point?
Rho 1, rho 1.
Just row 1? But then
Yeah.
you go up presumably row 2 and so on also, right?
Once rho 1 is, I mean,
So the one that first condenses, I suppose, is row 1.
yeah.
Lowest temperature.
Yeah, in the first, yeah.
Temperature.
Yeah.
I mean, you want to take, you're going to an optimum value, right?
Yeah, oh, fine, yes.
So
Yeah.
in that
Uh-huh.
gap,
Uh.
for where x equals infinity is that point there.
Where, sorry?
Here.
Here?
Yeah, from here to there,
Yeah.
something else can also happen, right?
Well,
But at
I'm just first fixing some phi value, and at given phi fixed value, gradually increasing the temperature, just one by one doing that. And I'm finding that it's least delayed here, so yeah. But well,
I'm just asking
Yeah.
f of x squared,
f
is that positive or negative?
f of x, what is?
I mean, this the second thing,
Uh,
f of x, the
Of
small
row
n
two.
equals 2.
coefficient of row 2.
Coefficient. At this point. At this point, rho 2's coefficient always positive because x is multiplied by some positive integers. The effective temperature appearing here is such that before rho 1 gets instabilized. In all this yellow region, all the higher rows are stable. Going beyond that, I don't know what will happen. Yeah, but it's clear that the confining saddle point is instabilized.
It's just that this f is some, I mean,
I see.
it's just that x squared is less than x.
Yes. So in the left region, you can trust that row 2 and row highs are all 0. Yeah.
So inside then things will happen.
Inside, complicated things will happen. It's very unclear. I mean, once if it's meaningful to trace this condensation, this saddle point at all, then all the other modes will condense. And for instance, in Shiraz's paper on Hagedorn transition, after this rho 1 condenses, all the other modes condensation has been considered to explain this gap, like Gross-Witten-Wadia-like behavior. So it's quite complicated. But anyway, at this moment, I've just showed the existence of the instability of confining saddle points. So before we reach that, something has to happen. Of course,
And this you say occurs at a lower temperature than the black hole
Yes.
ends.
Yes.
That's
Yes.
the
Yes.
point.
Yes. So, what can happen actually as a deconfinement phase transition? I mean,
And sorry, Ashok, I'll just verbalize why this is an upper bound. So suppose I choose this value of the chemical potential, then the effective potential has a maximum at rho 1 equals 0. So it goes down.
yes.
So it must go down. There must be something down there
Yeah.
to stabilize it. So there must be some negative energy, free energy solution.
Yeah.
And then
Definitely.
you can only do better if you go to some other.
Yeah. That's right. Yes. So what could actually happen for the deconfinement transition? One has to do more difficult calculation, but one can think of two scenarios. One can think of a first scenario at the condensation of rho 1 at this temperature that I've computed actually triggers the deconfinement transition. That is one possible scenario. And another possibly more likely scenario is that before we reach this temperature, below this temperature, actually a new saddle point might appear completely away from this confining saddle point, and then as we further increase the temperature, might take over the existing confining saddle point before it gets unstable. So in this case, the phase transition will have to be first order phase transition. This might be the case because the Hawking phase transition happening in the gravity dual is actually of this sort, right? So this, I suspect, might be the case. But to confirm this, one will really have to find another larger saddle point which gets formed before the instability point that I explained to you. And a room for that is existing because of the following reason. So,
Sorry, before you get to
Yes.
that, it's also if your intuition about this phase locking was right,
yeah.
then it almost seems that it has to be. Right? Because any non-zero chemical potential will ruin the exact cancellation of phases that happen at real chemical potential. So you would expect that at every imaginary value of the chemical potential, no matter how small, there was some phase of order n squared.
Mm-hmm.
If, because the phase cancellation will be obstructed to
Okay,
some
okay,
extent,
okay,
which means there must be some
okay.
solution.
Okay, yes, yes, yes. Yeah. By the way, below this instability point, if you just do the integral, the index you get is just product of infinite number of fxn's inverted. So it's simply the graviton index with chemical potential complexified. So in this yellow region, the complexification, I mean, at least in grand canonical ensemble, gives the same index with complexified fugacities.
Sorry, so, but
Yeah.
When comment is even in that region, there below 2.
Below?
Yeah, even when the red curve starts.
Yeah.
Yeah, yeah.
Even before that.
Yeah.
Yeah.
There has to be some new saddle point
There
because,
has to be, yeah.
because the precise cancellation
Has to be spoiled.
Mm.
But this one is not yet unstable. So his option one was that you get new saddle points because this guy goes unstable. There's a new minimum that occurs when this gets a new maximum.
Mm.
But that then would say that there were no saddle points down.
Yeah, 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 yeah.
It sounds like
Yeah, yeah. So that's the second scenario. But a possibility of allowing the second scenario is that, you know, now the matrix integral that you have to do, if you go back to the original matrix integral, if you insert the complex fugacities, the effective action is becoming complex. Okay? So if you're going to extremize this effective action, which is complex, you generally have to allow this eigenvalue living on a circle to deviate from the unit circle. Because action is complexified, the saddle points may be complexified. So what we'll have to do is more general than just investigating the distribution of eigenvalue on the unit circle. You'll also have to determine the shape of this deformed distribution on the complex plane. So so presumably the new saddle point conjectured in this scenario too will have two real functions: the shape function, say the radius as a function of the angle, and the distribution function. And at least as far as I can imagine, it will be a quite difficult integral equation. But if one can solve this and find a new saddle point, it will be a very great thing, I think.
But we would still expect the real parts of all these eigenvalues to be equal.
Real parts of eigenvalues to be equal?
Alpha is like we,
if you further increase the temperature to infinity, that will gradually merge to be infinity. But right before confinement, I'm not sure what will happen. Probably it's not maximally deconfining yet. Like, yeah.
And also the saddle point, the plane energy should necessarily go as n squared. There could be n also.
It should be n square, I think. You know, once it.
Giant gravitons and things like that also should contribute.
It will be important and much. Giant gravitons are objects of order n, right? It's just modifying the spectrum of graviton, reducing it, right? I doubt whether they will be playing an important role here or not. Yeah.
I think Abhijit was asking, can you take a limit of the index where only the chiral ring sector contributes? But there's no such limit. If I understood it.
Why only chiral ring?
That's the giant. This kind of giant gravitons. In the chiral ring sector, it's only giant gravitons.
But there are probably other less BPS giant gravitons also, right?
Well, there are less BPS giant gravitons, but then if there are also many more states other than those gravitons,
It's hard to isolate.
No, but that could happen only at high temperature. Let's say even below some temperature, it could be that giant gravitons dominate. 160 BPS giant gravitons dominate over 160 BPS black holes. So in that sense, there would be a sequence of transitions that could happen. Right?
Could that be visible at larger limit? So,
I mean, these giant gravitons at reasonable values of chemical potential, they differ from gravitons only because their charges are very large. Only when their charges are very large. Right, so it's like trace x to the m. If m is small compared to n, it's just a normal graviton. Now the kind of thing that would push you to making this giant graviton is to take some very large temperature. But when you do that, the black holes will come.
Is it clear that there is no intermediate?
I don't know. I think there will be in the microcanonical ensemble. It's not less clear to me that there will be in canonical.
I mean, what I just meant was another way of looking at was that if you compute the index for a very large value of n,
yeah.
okay, and compute the index for let's say 100 n equals 100 million,
Yeah.
they agree up to some t to the 100, right?
Yeah.
Shouldn't that be thought of as a giant graviton contribution? That's where they differ from the n equals infinity answer.
Yeah. Okay.
So if I were to reproduce finite answer,
Yeah.
then I would have to sum all these saddles,
Yeah.
coming with weight n
Sure.
in order to produce the right index, right?
Okay.
So those saddles should also be present somewhere.
Okay. Okay, good. Okay, so before finishing, I have a very, the final subject I'd like to discuss is the following thing. So I explained to you that the instability point of the upper bound for the instability of the confining saddle point is given by this fugacity. I'm going to finally compare with that with the known black hole solutions. I've explained to you that this point, had the known analytic solution for the black holes been the only black hole solution, this will be the one competing with the graviton saddle point, and that will determine the Hawking-Page transition, which is this point. Okay? So the inverse temperature for the changing sign of the known black hole's free energy is at this point. But inverse of this, the temperature, turns out to be higher than the upper bound of the deconfinement transition that we have found, which would be in a contradiction. Okay? There's no black hole which can cause the Hawking-Page transition below our upper bound. So this appears to lead, unless the argument we have made has a loophole, this appears to predict this appears to make another prediction of new black holes like saddle points, which should have lower Hawking-Page transition temperature and which should cause the transition below our upper bound, since the known black ones cannot do the job. Okay? And there's no signal that it should be Hairy black hole again, but at least these black holes, this contradiction has been found in the same sector as there have been studies on the Hairy black hole solution. So still, again, it will be interesting to see whether this saddle point is again a Hairy black hole or not. Okay. A final comment I'd like to make is about the Hodgson temperature. So in the analysis of the weakly coupled partition function of Yang-Mills theory, not the index, but partition function. So the partition function just sensitively depends on coupling, but Aharoni and Shiraz, Marasano et al. Have carried out a weakly coupled analysis. And in this case, it was happening that at real fugacity for temperature, it was happening that the appearance of this instability of a confining saddle point was preceded by a Hodgson-like growth of density of states, which is roughly the following. So if you consider the real fugacity x, it is the temperature, in the confining phase, rho is all around 0. So if all x's are positive, the large n partition function, let's say, will be given in this way. Okay? So, but since this is all real, when any of these coefficient f changes sign, let's say x, so the mode with n equal to 1, whenever it changes sign, it first has to diverge. Okay? So that diverge has to do with some large number of density, exponential growth of density of states, and it actually has been analyzed to be the Hodgson behavior. Okay? But however, at strong coupling, this is a weak couple analysis. However, at strong coupling, we expect the Hodgson temperature to be expected to be given by the string scale, just like the Hodgson temperature in the flat space, much higher than the deconfinement temperature. So in this case, in the strong coupling limit, we don't expect the local instability point of the confining saddle point to be locked with the Hodgson temperature at all. Okay? So we don't expect such behavior, for instance, in the index, because the index is independent of the coupling. It should respect all the strong coupling expectation. Interestingly, the result we found is consistent with that, because we only investigated the sign change of the real part, while the imaginary part of x remains finite. Okay? So we have found an instability without causing the confining phase partition function to diverge. So it is not related to the Hodgson temperature as expected. Okay? So that's one small comment that has to do with the instability analysis of the index. Good. So, well, today I made it on time. So let me just summarize what I have done today. So I've firstly explained to you that there is a signal of deconfinement that can be captured from the index, which I explained to you by finding a local instability of the confining saddle point.
Sorry, could I?
Yeah, sure.
Suppose I go to the place where your values of chemical potential for which which when you turn on a complex part of the chemical potential, the gas looks unstable.
Mhm.
Now, does it mean that the full graviton partition function should be ill-defined at those values of chemical potential?
No, I mean, just by staring at like this graviton part, this in the index, the real part changes sign, imaginary part's fine. Just this expression, if it's expanding fugacity, I don't think I find any problem. Yeah, if you just stare at this expression.
But now suppose I just compute the partition function by Bose exponentiating gravitons.
By both.
By Bose exponentiating gravitons.
Bose exponentiating, yes.
I was wondering whether
Yeah.
you're saying there's no problem, but there is a. I see. You're saying that because this chemical potential, you expect to see nothing funny in that partition.
Well, I haven't found anything. I mean, actually I was concerned that whether the expression is seeing the Hadron-like behavior because I wanted it not to see.
Yeah.
I didn't. I mean, apparently, as far as I could see, I could find nothing very special at this instability point. But I think all I did was just finding that fugacity expansion and extracting out degeneracy. That seems to be of no problem.
Could it be that one of the?
I was suspecting whether the convergence, Hadron transition, I expect has to be the radius of convergence, right? This.
Yes.
But I found no signal that the radius of convergence problem appears here, and it just looked fine, at least as far as I could see at this point, the upper bound point. Yeah.
All gravitons have x plus q positive, right?
Yes. Yeah. X plus q. Yes.
The thing with which you're weighting the chemical.
Yes.
All of them. Sorry, j plus q. J
Yeah.
plus q.
Yeah.
Positive, right?
Yeah.
So there can be no problem.
Yeah.
So you're saying you just don't see any evidence. If I just look at the full partition function of gravitons, it's not becoming sick in any way.
I couldn't see that.
Yeah.
I couldn't. Only when you stick to this matrix model, this distribution, I some sort of see. But
It's interesting.
yeah, I mean, yeah, it's a bit puzzling. Yes.
Why would we have expected such a thing?
We expect what?
Why would we have expected such something?
Divergent or something?
Some graviton.
In the free theory calculation Shiraz did, the breakdown of this confining saddle point is locked with the this Hadron temperature, at which the density of states as a function of energy exponentially grows, so that the partition function actually diverges. Here in the graviton, that kind of thing I didn't want, and I don't find. I don't find any other pathologies. I mean.
But if you compute the determinant, and let's say you compute the determinant of rho 1.
Determinant of rho 1. Determinant is what?
I'm sorry. You compute this f. You're going to use a formula to get. You're going to use to get from the first line to the second line. You're going to use the formula e to the power minus a x squared.
Yeah.
Integrated as 1 over square.
Yeah.
Okay. Or maybe e to the power a x bar is 1 over a.
Yeah.
Now that formula is only correct with the coefficient, with the real part of the coefficient of that
being
is positive.
Yeah.
But aren't you saying here that the real part of the coefficient is going negative?
In the index, it goes negative.
Negative.
Uh-huh.
So that to go from there to there is a bit suspicious,
Right. Yeah, definitely. So if you're going to derive result from matrix integral, it's suspicious. But if you stare at the final expression without knowing the source, I don't know. That's what.
But that's the intuition. That something the integral should start exploring.
Yeah.
Should see something funny out there.
Yeah.
It wants to go far.
Yeah. Anyway, that's the funny situation. Yeah. So any other? Okay. So just to conclude.
So the temperature that you have is much less than the Hadron.
Yes. Actually, I've seen some people working on integrability in AdS that Hadron temperature is actually at strong coupling is behaving as expected. The string scale of the strings propagating AdS. So it's much higher than Hadron temperature, which is order 1 in the AdS radius. Yeah. So yeah. So but a notational mistake is happening here because I've denoted all these upper bound as omega h and xh. I blindly believe the connection with ignorantly believe the connection with the confinement and Hadron, and just carelessly first wrote this as Hadron temperature in the initial draft, and realizing that they have to be different, I didn't find any other subscript to find, so this H actually means hydrogen in my initial draft, but I mean, this is X sub H, T sub H is still kept in my paper. Yeah, but anyway, it's not hydrogen temperature. So anyway, I try to explain the local instability of the confining saddle point, which presumably sets an upper bound for the deconfinement transition temperature. And also I explained another evidence that a new black hole-like saddle point should exist by finding the McDonald index in the large N limit and finding the large N saddle points similar to the black hole saddle points where known black holes are expected not to exist. Okay? This is the content of my talk. In the next lecture, I'll do basically two things. I'll try to develop the Cardi-like free energy of the even-dimensional superconformal field theories indices using more abstract argument based on Tooft anomalies, on discrete symmetries, and so on. Because if you remember the form of the Cardi free energy I explained to you for four-dimensional Yang-Mills theory, it's expressed in terms of anomaly polynomials. Okay? So I'll do this abstract derivation of this free energy using some background field theory technique. And similar technique will be applicable to some non-Lagrangian theories, let's say 62-0 theories. I don't know how to say, but maybe it almost derives the Cardi free energy of 62-0 theories, but with some logical gaps that has to be filled in. So I tried to explain to you that yesterday. I'll try to explain that tomorrow. And the computed almost derived free energy will successfully count large AdS 7 black holes as well. Finally, I'll explain to you some similar business that you can do with odd-dimensional CFTs. Again, I'll be deriving some Cardi-like free energy of these CFTs, but now using much more dynamical information and try to explain to you some more exotic kinds of deconfinement-like behaviors and also address them dual black holes. Okay, this is it. Thank you.
Any questions at HRI?
Questions? No, not at the moment.
Hello, ICDS? Is ICDS there? Any questions if you are there? How about here? More questions? What's your?
The supersymmetric black holes can they be made arbitrarily small?
Arbitrarily small. I think so. Yeah. You mean the known black holes? Yeah, but they run into small black hole branch. But I think in microcanonical samples they should be fine. Yeah.
So at least in this limit,
Yeah.
possibly more, but at least in this limit, I think the superradial criterion should be good.
Yeah.
Anyway, let's talk.
This charge and energy thing.
Yeah,
Yes.
yeah.
Okay.
At least in that limit. You know, you might worry that if the black holes are big,
Yeah.
then you don't know the
Mhm.
the value. Even that is probably okay because of supersymmetry. That you know, discrete charges don't get renormalized,
Yeah.
and then DPS fixes it. So it's probably okay. But at least when it's small, because of form factor,
Yeah.
it should be the right criterion, I think.
Okay.